All right, hello everybody. Welcome to calculus, and we're going to be talking about section 5.3, which goes over the fundamental theorem of calculus. And as the name clearly emphasizes, this is a very important theorem. It's fundamental. It's one of the most important theorems of calculus, and we're going to go over part 1 and part 2 today. There's actually a video at the beginning of this section that I would recommend watching if you guys are interested in that. And it helps go through the first part and the second part with different examples. So let's talk about part 1. So it's saying if f is a continuous function on a, b, then the function g defined by g of x, and we're going to let it equal the integral from a to x, where a is a constant value of the function at t, dt, and it's between a and b, is continuous on a, b, and differentiable on the open interval a, b, and the derivative of g is going to be equal to f of x. So what's that telling us? Well, if we want to find the derivative of g of x, all we have to do is take that x and plug it into f of t. And remember, that's only when we have a constant to a variable x. Then we can just plug in x into this function, and that's our derivative. So pretty much we're undoing the integral by taking the derivative. So it says right here that the derivative of a definite integral with respect to its upper limit is the integrand evaluated at the upper limit. Alright, so let's look at an example of this. So we'll scroll down, get an example. Well, here's a pretty basic example. So let's say we want to find the derivative of the function g of x, and we're looking from 0 to x, and we have the function here, so the square root of 1 plus t squared dt. Well, let's say we want to find the derivative of the function, so we take the derivative of both sides. If we take the derivative of this side, all we have to do is take an x and plug it in to where we see t. So that's how we find our derivative of our function. So this is pretty great. We just have to keep in mind of the format of our theorem, right? It's a constant at the bottom to a variable. Now let's say in the video, so for example, in the first video at the beginning of this section, they give us an example where it's x to 0. Well, how do we rearrange that so that it looks like what we want? We want it a constant to a variable, not a variable to a constant. So the example they give was, I believe, from x to 0, but it was the same function. So to switch that, to switch a and b, all you have to do is put a minus sign out front. So if you have a problem like that, that's where you would have to use your rules for integration to help solve that problem. So this is this example I want to go over because it tends to come up quite a few times. It's just using the chain rule. So we're taking the derivative of both sides, but notice how we do have a constant at the bottom, and remember this could be any constant at the bottom. So 1 is fine, 0 is fine, any other constant is fine. But this time it's to x to the 4th, so we have to use chain rule. So when we take the derivative of both sides, we have to take the derivative of the inside function too. So we are letting u be equal to x to the 4th. So we have u here. We just replace x to the 4th with u. You can pick any letter. They picked u. So we have our So we're taking the derivative of this function right here, and we can use fundamental theorem of calculus. So we have the derivative, but then we have to take the derivative of the inside function. So we're using fundamental theorem by just plugging in u. So we have secant u, but we have the derivative of u. So we have secant x to the fourth times 4x to the third. So that's one of the trickier ones using the fundamental theorem of calculus, but that's about as difficult as it's going to get for the fundamental theorem. So hopefully you're okay with that example, and maybe putting a negative sign out in front, but other than that, I think it's pretty straightforward. So this is where we get to the exciting part, the fundamental theorem of calculus, part 2. So for this, we're looking at the antiderivative, so similar to our last exam that we took. We had our last question about antiderivatives. Well, this time you're going to be applying it, because now we know that the antiderivative is the same thing as integration. So for this, we're going to be taking the antiderivative, but we're plugging in the variable, we're plugging in the constant b, so we take the upper bound minus the lower bound, and that's how we get our derivative, or our antiderivative. So for this, we're looking at, let's see if we can find an example. Okay, so this is a great example. So we're integrating from 1 to 3, and we have e to the x, d of x. So all we have to do is first find the antiderivative. So what's the antiderivative of e to the x? Well, it's just e to the x. So we have our antiderivative, and now we're plugging in our bounds. So it's going to be 3 and 1 that we're plugging in. So right here we have the antiderivative at 3 minus the antiderivative at 1, which is the same thing as e to the third minus e to the first. So this is your final answer right here. Okay, so right here we're finding the area. Finding the area is the same thing as integration. So we're finding the area under the parabola, and we have y equals x squared from 0 to 1. So we're taking the, we're integrating, taking the antiderivative. So what's the antiderivative of x squared? Well, we have to use our antiderivative rules. So we add 1 to the exponent and divide by that new power. So we have 1/3 x to the third, and that's our antiderivative. And then we have to plug in 1 and 0. So we have, so this bracket right here, they use this to symbolize what we're plugging in. So right here we have our antiderivative, and we're plugging in from 0 to 1. They just symbolize it using this bracket. And they have 1 to the third over 3 minus 0 to the third over 3. Remember, it's always f of b minus f of a. And that keeps you 1/3. This example, it might seem a little tricky, but it's not too bad. It's just written a little bit different. So we have 3 to 6 for our integral, and we have dx over x. Well, we can rewrite that. It's the same thing as 1 over x times dx. So this is the same thing right here. Well, what's the antiderivative of 1 over x? This one's a little tricky. To help you figure it out a little bit, maybe try using the power rule and you get dividing by 0, which is illegal in math. So you know it's going to be something special. So the antiderivative is actually ln of the absolute value of x. And we're looking from 3 to 6, so we're plugging in 3 and we're plugging in 6. So we have ln of 6 minus ln of 3, And if you remember your natural log rules, it's the same thing as 6 over 3, which is ln of 2. So when you subtract ln's, you can combine them together by making it division. If you add them, you can combine them together and make it multiplication. So it depends on what that symbol is in the middle. But so for you don't have to simplify it down all the way, but if it asks you to, then you might have to use some natural log rules. So notice that differentiation and integration are inverse processes. So make sure that you have the fundamental theorem of calculus in your notes. That's super important, and it'll be really helpful in the future. So make sure you have this part written down. And that's pretty much it for this section. So if you have any questions, let me know. And then your quiz will be on Friday. And I'll be on WebEx if you guys have any questions on any of these problems.